Okay. I think the meeting's recording, which means that what we go over today should be saved. Hopefully I'll be able to post it to the Canvas page pending any privacy or like whatever concerns. So I'll have to confirm with Professor Blaze. Thank you all for being here. This should hopefully be time for us to discuss. We don't have a weekly discussion, but if you have questions along the way, just unmute. You can ask me anything at any point. I'm going to walk through some simple linear programming using Python and how you can do that straight from your machine without having to download MATLAB or any other software. I'll get started here, and then I'll sort of try to direct this in a direction that makes sense for you all. So to make sure that what I'm doing reflects what you want to see and what you want to know how to do. Okay, that is not the screen I wanted to share. Those are my notes. Instead, we will share desktop too. Okay. Can you all see my empty Chrome tab?
Yes.
Beautiful. Okay. So the first step when writing these linear programs is you're going to want to go to collab.research.google.com. Right. And then this link you can do out there with your Google Drive. Anyone can go there. Once you open this up, you're going to have this menu in front of you. You can open up recent notebooks or you can click on new notebook. Once you have a new notebook open, and if you all want to, you're more than welcome to follow along with me. I'm going to try to go pretty slowly and give you time to digest so that can give you a good chance to make sure you're understanding what's happening. So this here operates sort of like just any other Google document, except instead of writing docs or a sheet, you're instead writing a Jupyter notebook or a .ipynb file. You can rename it to be what you want. So we can call this linear programming tutorial. Right. And then if at any point, once you're done writing, you can save it. You can send it to GitHub. You can also download it both as a Python file and as a Jupyter notebook, and then run it in VS Code on your local machine. But this here gives you a chance to run things straight off your computer using Google Drive. It's a little slower than things like VS Code, but it's much more convenient. The way that the Jupyter Notebook works is that you can set it up where you'll have blocks of code. So for example, here's a block of code, and we can do something like print hello world. Right. And then that's going to run. It's going to take a moment to think. And I really hope I have Wi-Fi because yes, I got Wi-Fi the other day. Okay. So that's how you can write code. And then when you're ready, you just press the play button here. You can run the code you've written. You can also create text. So for example, you can create a text block and then you can format that in different ways you want. So right, bold text, you can do comments. You can really set this up how you want. It's written using LaTeX code. LaTeX is a way where you can write to do cool math text. So for example, when you look at your homework and all the equations and problems are written out nice and neatly, that's done in LaTeX code. And you can write in LaTeX both here in Google Colab, or you can also do that in Overleaf, which is something I might do another webinar on next week, depending on how well this one goes. So you can write using code and text. The other important thing is that, let's say you have multiple code blocks, so long as your runtime doesn't disconnect, like you don't refresh the page or wait too long, if you define a variable here in one block, right? And then I run this block and the variable x equals 5 is defined. Then in another block, it's going to remember those variables, which means that variables and different linear programs are, and really anything is saved between different blocks of code, which is the other important thing here. If you decide to do it in different code blocks, maybe you want to do your commenting with one of these, it lets you split it up and it's super helpful for debugging. Any questions on the basics of opening up Google Colab, starting to write Python code or variables and text and what our interface looks like? I see a thumbs up. That's good. Okay. So what we're going to do now is the first thing that we want to do is that Google Drive has a lot of libraries that we can import. And then when we want to import those libraries, we can use them, all of their functions in our code. Some of the libraries are not automatically saved in Google Drive. And in this case, we're going to have to install them. And we're going to have to reinstall these libraries every time that we want to create, refresh the runtime. One of these is the Pulp library. The Pulp library is not immediately accessible. So what we're going to want to do is we're going to want to do exclamation mark and then pip install Pulp. And Pulp stands for Python using linear programming. So we can hit run on that. And then it's going to load in the Pulp library into this runtime of Google Drive. So you'll have to do that like if you open up a new linear program. That's one of the downsides to doing this online in Google Colab, because once you have it downloaded on your computer, then you can use it forever. So if I'm coding in VS Code, I don't have to run that line every time. But that's just a line that you need to have at the top there. So the first line we want now is that Pulp is installed. We want to import Pulp. This is going to let us use the Python using linear programming library. All right. So now the big idea is we want to create a linear program. And I hope from our last couple of days in class, we've gotten the idea that we have a linear program, right? This is the same as an optimization, a linear optimization problem, right? And this linear optimization problem is going to have an objective function, which is something we're trying to minimize and maximize, or maximize. And we're also going to have a number of constraints, which use linear variables and constrain the values of our decision variables. Are there any questions on the format of a linear program and what that looks like? We've gone over some examples in class the last 3 days, but if you have questions, this is also a great time for me to help fill you in there. All right, so what we're going to do then is we are going to create a linear program. In the Pulp library, the linear program looks like, see someone in the waiting room, admit there. In the, what was I saying? So in the Pulp library, we can treat the linear program like a variable, right? And we're going to define it sort of like that. So we're going to say LP, I'll say sample LP problem. We can call it whatever we want. That's the variable name. And we can already see that it's trying to autocomplete for us. I think Google Colab has some AI having to do that. But we're going to want to start with Pulp. That tells the computer that we're calling from the Pulp library and that we're going to try to use it. And then, right, we're going to use LP problem. So this is saying from the Pulp library, we're now going to create a linear programming problem. And we can call this whatever we want. In this case, I think we can call it tutorial problem. And then that's how we refer to it, right? So that's going to let us give a name, and then we can uniquely refer to it with that. All right. Then from there, we need to tell it if we want this to be a minimization or a maximization problem. So in this case, we can say pulp.lp maximize. So we've now defined this linear program inside of the Python library. So it now exists. And now what we can do is we can add constraints. Well, we can create variables, an objective, and a constraint. So we need 3 things. We need Oh, and for anyone new to Python, if you want to leave a comment, you can use the pound symbol, which I've done here. And that means that anything you write on that line won't be read as code. It'll be read, just skipped over by the compiling engine. So we need variables. We need an objective. And we also need constraints. Okay. So in this case, we can keep it pretty simple. We can have a variable x. And then again, we need to call the Pulp library. We already have an autocomplete right here. So you can even hit tab, and then it looks like Google's AI will complete that for you. But for the purpose of example, I'll sort of just walk through what each of these mean. So when you write Pulp, that's saying we're looking at the Pulp library, we're looking at linear programming, and this is going to be a linear programming variable. So we're saying what we're creating, right? Just like up here, we created an LP problem. Here we're creating an LP variable. And give me one moment, I have a knock on my door.
Hi, Lizzie.
All right. That was one of my friends. So we then have a pulp.lp variable. And then what we're going to do is we need to give it a name. So in this case, we can just call it x. And then we can give it a lower bound. So we can say, put a minimum on it. And that's going to be important when we're doing our problems. So in this case, a lot of times we're going to say that x is going to be greater than or equal to 0. If we want to, we can also put an upper bound on it, but I don't think that's not always going to have to happen. But if you need to, could put an upper bound, but usually put a lower bound and then use constraints for upper bounds. That's usually how the standard form of a problem works. And then from there, we need to give it a category. There are 3 different categories we can give it. We can give it to be continuous. We can give it to be, I'll say, when we create a variable, it's either going to be continuous, binary, or integer, right? So in a linear program, it's always going to be continuous. But in a field of optimization known as integer programming, then we could end up having integer variables or binary variables. Binary variables are helpful in cases where we have like whether we do or don't do something. And the other variables, continuous, are helpful for, maybe, right, like how many trees, or I guess, like how long of a plank of wood should I make, or that sort of stuff. So a lot of times the world is in integers, but in this case, we're working with continuous. So we also have a variable y, which Google's autocomplete so helpfully created for us. And we now have x and y as our 2 linear programming variables. And in this case, they are both continuous. All right. Any questions so far on creating variables? Okay. So then the next thing we're going to do is we're going to create an objective function. So the objective, as we learned during class, is essentially the sum of variables that we're trying to maximize or minimize. In this case, we've defined this as a maximization problem. So we can set this up and we can say sample LP problem. And then we're going to say plus equals. And it's already giving us a suggested autocomplete. We can make that what we want, but we can also say, right, 3x plus 2y. And then we can call it objective function. This autocomplete is taking away all my fun. It's spoiling my lines ahead of time. So we now have an objective and we now have variables, right? We're trying to maximize 3x plus 2y. Now we want to add some constraints, and we already have a few sample constraints created by AI. And what we're going to do, right, is you can name sample LP problem, and you want to make sure that you're referring to that same problem name, right? So when we say we're referring to sample LP problem, that's how it knows that we're adding it to this specific linear program, right? And we can just let it do a little autocomplete. The constraints are pretty simple. We've talked about those in class before. So in this case, we've said that 2x plus y is less than 100. We said that x plus y is less than 80, and x is less than or equal to 40. So we've now created these three constraints, right? And now we have a linear program, which means the only thing left to do is to solve it. So means type in here, and you all can see what I'm typing, right? I don't see the green square on my screen, but hopefully I haven't been talking into the void. All right, I see a thumbs up. Perfect. Okay, so we already see this here. Oops. We're going to name the problem, and we're just going to use the .solve method. All right. And we already have a whole new autocomplete, which we input in there. AI is very good at this, especially for simple linear programs. ChatGPT is super helpful for writing linear programs if you know what you want to happen. It's not very good at checking whether you solved them right. A lot of the work you're going to be doing later on in this course is solving linear programs by hand and doing the linear algebra that makes that happen. And I don't recommend asking AI to do that. It usually does it wrong, and it gets you caught up in some weird fractions, and it's generally not fun. At least that was my experience last year. I don't know if it's gotten much better since then. Once we have finished writing our program, right? And I'm gonna do this manually just so I can walk through each part as we're doing it. So we want to print the status of our program, right? And this here is just a print statement. And then the nice thing about print statements in Python is you can concatenate both a string. So this here is a string where we say status. And then we want to get the pulp. LP status is one of the functions included in the pulp library. And then we can get that of just the sample LP problem .status. All right, so I'll hit run now. We've created variables, we've created an objective, we've created constraints, we solved the problem, and now we are outputting the results of that solution. Oh no, name sample linear program. And that's where we need to be careful that we're using the right variable names. That mistake was not on purpose, but it's a good teaching moment that we need to make sure we're being consistent with our names across all parts of the program. So this here reads that the status is optimal, which means we found a solution. Now, the next big question is, what is that solution? It looks like the computer already has a great idea for how we can do this. But again, I'll type it out so that we can just be extra clear on how we're doing it. So we can go for variable, and we can actually put whatever we want here, right? So we can say for results, right? We can call it what we want. It's just, that's what we're iterating over. And then we just have to be consistent to make sure that this here matches with what we're iterating over in the next line. So we can say for results in sample LP problem dot variables. And then we always need to have a colon here. That colon tells tells Python that we are now entering a for loop. The way that Python reads for loops is with indentation, which means that we say a for, and then we have that colon right there. Starting on that very next line, we indent, and then once we're done with our for loop, we can end the indent, and that means that the for loop is over. So everything that I indent here, however many lines I want, that will be repeated every single time for each variable in the sample LP problem. So now that I'm in here, I can do a print. And I can say, result stuff name is equal to, oops, is equal. And remember, in order to make this work, we need to have a comma right here, since we're concatenating both a variable with a string, and then another comma here, since we're concatenating it with another variable. We have results dot var value. And so what this line is saying is we're creating a simple for loop, and we're saying for each of the variables, so x and y, we're going to print the name. So we're going to print x, right? And then y. And then that should just be an equal sign, right? So we're going to print the variable name, which is x for start. And then we're going to print equal sign. And then we're going to print x's value. And then we're going to repeat that for y. We're going to print y, the equal sign, and then the letter y. All right. So now that we've put that together, we should be able to hit run there. And we get our optimal values. And we see here that, did we end up on this constraint? Yes, we did, since we have x is 20, y is 60, which means that we have 40 plus 60. We're right on that constraint, equal to 100. 20 and 60 also got us right on this constraint. 20, we didn't hit this constraint, which means that there's some slackness there. We'll learn more about that later on in the course. So the other thing that you might be curious about is what's the value of the objective function, right? What's the profit? What's the margins? And then looks like AI is already helping us out here. And the way we can do that is we can do a print, and we'll say objective value, right? And then here's a string we're going to concatenate with the value, and we're going to print out pulp dot value. So we're turning the value of the sample LP problem dot objective. All right, and we can run that, and we get our objective value. Any questions on creating and solving a simple linear program in Python? Okay. This will be super helpful on your first homework. If I open up our Canvas page very briefly, we can take a look at under your assignments. I believe this is due Thursday evening. Right here, use either Microsoft Excel or MATLAB Solver. I'm pretty sure you could use the Python solver now that we've done this webinar. I'll ask Professor Blaze. But look at how easy this can be to solve a linear program, right? You just plug in your variables, plug in what exists right here, and then you get your solution just like this, and a couple lines of code. You hit run, it's on Google, you don't have to download any software. So that's going to be super helpful on your first homework. Later on in the course, you're going to be solving by hand some complicated linear programs. But now with this, it's going to be super duper easy. The solution, you're still going to have to do it by hand, but to check your answers, it's going to be super duper easy. Okay, I have a little more, which I think could be fun to talk about. I'm going to introduce a little more of an advanced example. And I won't get this to load though. All right, and this one, rather than type it out along with you, I'm going to paste it in. All right, so let's take a look at a more advanced example, and we're going to sort of talk through it and see what happens and the different things we can do with a linear program. So in this case, we're now going to create extended LP problem. And this is now a minimization problem. So that's the other thing we can do. So you can do minimization or maximization. Then here, and actually what I'll do is I'm going to share this code in the chat, just so that you can have it in front of you also and start playing around with it. since I don't want anyone to be like scrambling to type along or keep up the example. All right, feel free to take that. You can make a copy or paste it into your own collab notebook. I'll give you maybe 15 seconds to load that, and then I'll continue on with our example. Okay, let's continue. So we now have a linear program with 3 variables. You can really create as many as you want. One of the bigger projects I worked on was for the math department, and that one probably had, I don't know, over 1,000 variables, and it still runs in half a second. So linear programming is really powerful. You can have continuous, integer, or binary variables. And then we have our objective function, right? It's a simple minimization of adding positive values, right? And we have lower bounds here, but they all have to be greater than 0. Then we have our constraints, right? These are just simple linear programming constraints. We notice also that we can have greater than equal to or double equal sign. It's very important that you use the double equal sign. The single equal sign in Python is used for defining variables. So up here, notice we've defined the variable x, but down here, where you haven't defined a variable, we're instead testing for equality using the double equal sign, right? And then we can solve the problem and we get to the optimal solution. The next thing we can do is, this here is all things that we've done before. So I'm actually going to comment out this for now, just to show what that looks like. Right? We create our linear program with our objective function minimized to meet the constraints with an objective value of 7. All right. Now, one thing you can do is, let's say you have your results and you want to save them to a CSV file, right? If you want to save these to CSV or Excel, that might be super helpful if you want to share, share your results. If you maybe say you have your group project and you get your results and you need to do an analysis with them and you want to get them to an Excel file, this is going to be super helpful. So what I've done here is, what have I done? I've created, make sure I put that right. So solution is a dictionary in Python, right? And the way that Python dictionaries work is that you're going to have a key and a value. And what we've done here is we've created a dictionary where each of my keys are my variables. So I have a key X, a key Y, and a key Z, right? And then I've printed it, and then I've attached this key to a value, right? So the key unlocks the door to a value. And so, and it can unlock the door to multiple values too. But in this case, each variable only has one value associated with it, right? And so then, right, the solution, I'm now creating a new key called objective value, and I'm just putting in the objective value there, which means now, after this line, I have a dictionary called solution with the values X, Y, Z, and objective value. And these are my keys. And then each of those 4 keys have values to them, which are these numbers here, 7, 0, 0, and 14. All right. Now we're using data frames. I'm a data science major, and math, but this is where my interests come in. Up here, we imported the pandas library. We don't have to install anything with pip to use this, but we're going to want to import pandas as PD. Pandas is a library that lets you work with and manipulate data frames and different, like, I guess, like database or a data frame. It's essentially a matrix of information. That's what a data frame is. And we're importing it as PD. Importing pandas as PD, this makes it easier because instead of having to call pandas every time, we just have to call PD. You can do the import whatever you want, right? You can import pandas as pan, but then you just have to make sure that you're, calling pan each time. But generally the convention is to import pandas as PD. So that's the convention, right? Import pandas as PD. And then here we can say that solution data frame, solution DF, we're defining a new variable is equal to a PD data frame, where we have, should I get this right? Yes. So I have two columns, variable and value. And then that's essentially going to be the items under solution. So what this line of code is doing here is it's essentially creating a data frame where you have variable and value, and we're putting under it the dictionary from solution, right? So we're reading solution and we're calling its items. And we're putting it under the columns variable and value. This line here, we have solution data frame .to CSV. The .to CSV file comes from pandas, and we named the file we want it to go to. And then we don't want the index column. This is saying that we don't want a column at the start, like with the index of everything. All right. So let's see how this works if I hit run. And then here I now have lp solution.csv, which opens up here. And I can even download this if I want. And I now have a CSV file of my variables, their values, and the objective value function. And if I want to, I can also do .to Excel. Oh, maybe I can't. Oh, I know. It's because I need to go to XLSX. Oh. Right. There we go. It was with the file extension. The file extension needs to be .xlsx there. Okay. And then in a moment, it's going to pop up here. All right. So the next thing, and I want to look at, I have two more main things I want to show you. One is infeasible problems, and the other thing is, what do you call it? Oh, plotting. Okay. So I'm gonna make this a second code block here. I'm just gonna paste that since that'll make it easier to keep these separate. Okay. So this is now a linear program, and it's been designed to be infeasible. That's why we've called it infeasible linear program. You can look at this and you can see for yourself that it's infeasible. I won't go through the specifics, but there's no values of X, Y, and Z that meet all three constraints. All right. So I'm gonna comment this out for now. And if you want to comment out a big block at once, you press and hold command, and then you use the backslash button, command backslash. So notice here, status of infeasible problem is infeasible. Now, if it's infeasible, what we can do is we can find what's called the irreducible inconsistent system, or the IIS. And what this is if it's infeasible, which it is, right? This is going to happen. So it's going to print this line. And notice how we index. So we're in the if statement, and then we indent further in. Now what we're going to do is we're going to go over each constraint. And we're going, let me see. Let me make sure I explained this correctly. Okay. So what we're going to do is we're going to look at each constraint, right? And what we're trying to do is we're trying to find a minimum cut. We're trying to find constraints that exist that are making this infeasible. So in this case, I've created a temporary linear program called infeasible linear program temp. And it's a copy of the infeasible program. So it's the same thing. I then pop, so I remove that constraint. So I iterate over each of my constraints. I try removing it, and I try solving it. And here I'm saying that if it's not infeasible, so I have the exclamation mark equal. If it's not infeasible, then that constraint is part of an irreducible infeasible system. This doesn't come up in the course. This came up in my research over the summer, but this is a good way for you to check if I got rid of this constraint, would it be feasible? And if we run it, we notice that if we get rid of just constraint 1, then we would be feasible, or if we get rid of constraint 3, then we'd be feasible. And we can even try this, right? So if I go in here and I get rid of constraint 1, it's optimal, right? Same thing here. If I get rid of constraint 3, it's optimal. But I'm willing to bet if I get rid of constraint 2, it's still infeasible. Any questions on irreducible inconsistent subsystems? Identifying constraints that are singular blockers to finding an objective function that works. Are you all following? Does this make sense so far? I hope this isn't way too advanced beyond your Python knowledge. See a thumbs up. Okay. If any of you have questions, feel free to leave them in the chat or unmute. The session really is for you and for your peers. So please just, let me know if I can support you there. Okay. So the last thing I'm going to do is I'm going to plot, or I'm going to paste in more code. And that code is going to go right here. Okay. Feel free to reaccess the link that I shared with you to copy over this code. Actually, wait, that's not quite done yet. Do not copy that code, I think. I'm stealing like bits and snippets of code from my planning document, so I just want to make sure that I'm getting the right thing for you all. Okay, I need one more line. I notice how indentation gets really important here. Okay, this should work now. Feel free to copy over my code. All right, so the next big thing we're looking at in Python, the NumPy and matplotlib libraries. We're importing these again as NP and PLT. So whenever you see those come up, that means that we're calling those libraries. We're now creating 2 functions, and functions are super helpful because they let us write repeated blocks of code, so that instead of writing the same block of code over and over again, we can have a function. And we do that by defining it. So we say def, name the function, and then, the variables that we take into that function, separated by commas, right? So in this case, I have 2 functions here. One is called plot constraint. The other one is called plot feasible region. And then all I'm doing is I am plotting the feasible region, right? So these don't actually do anything until you get down here and you leave the indentation, and I say plot feasible region with no inputs, right? And if I had an input, I would put it in, right? But no input variables, so that gets sent right up here. And then here, I'm creating a figure. I'm plotting my constraints. Are creating constraints, right, with different names, right? Create the border on the plot. And actually, there should be a linear program to go along with this, shouldn't there? Okay, there isn't. But we can see that this would correlate to a linear program, right? Actually, it's the same one as above. No, it's a different one. right? And then when we run this, right, it can help plot our feasible region. So using this as a template, it should give you what you need to create a graph. And then notice here, so blue, we have x plus 2y less than equal 10, which means that our feasible region is inside this blue zone. 4x plus y is greater than 5, which means it's outside of this green zone, which means we're now on these two. Looks like we're less than 7, which means that our feasible region now looks like this, right? And then we add in our fourth constraint, less than equal to 6. And we now have our very nicely drawn feasible region right here. Not technically shaded in, or shaded in against everything else, but this is super helpful for some of your early homeworks. And I think, at least on last year's midterm, one of the first questions was plotting a feasible region. So that's going to be helpful. Okay, so that's the big idea on linear programming. We talked about importing Pulp. We talked about creating a problem and then solving it with an objective constraints and variables. We talked about more advanced options and different ways you can customize your problem, and then ways where you can see which constraints are making it infeasible using the irreducible inconsistent systems. Then from there, we moved on, and is that repeated? No. Right. And then we talked about graphing. Graphing is less my strong suit, but it's not super hard to take this template and play around with the NumPy and Matplotlib libraries in order to create graphs. Okay, those are the big ideas. How do we feel about linear programming?
Teddy, I have a question.
Go for it.
Do you have an easy way to find the corners for that feasible region?
The corners for the feasible region.
Yeah, so like the intersection points or the corners.
Yeah, for sure. So in this case, I don't have code yet that can do that. But for example, one thing that might be a super helpful tool is using AI here, right? So I wonder if I could go in here and I can ask it to generate with AI, and I can say, write code that will supplement my above block of code by identifying the corner points of by identifying the corner points of the feasible region. And then I might actually even just paste this in. Oh no, I just limited on text. Let's see how that goes. But a lot of times you might just have to look at the problem, but let's see what AI came up with here. So intersection of constraint 1 and 2, we get x equals 0 and y equals 5. That is an intersection point. Constraint 1 and constraint 3, x equals 4 and y equals 3. Right there. Yep, right there. There's an intersection point. And I'm going to trust that the rest of these are the right intersection points. So that's one way to do it. It really comes down to algebra, so you might have to do that by hand sometimes. But in this case, AI can be a helpful tool. Just remember that as per the course syllabus, if you do use AI, to include the prompt and response as an appendix to your work, right? You're allowed to use it. In fact, I encourage you to use it. This is a super helpful tool. It's helped me with a lot of my research, but you just want to be careful to make sure that you're following the course requirements, and that if you do something like this, to just include this as an appendix to your work. I know with ChatGPT, you can also get like a link to the conversation and then just paste that in. And then if you put that in, then rating it, I have access to the conversation you have. But finding the corner points just comes down to algebra and solving for where these intersect, which is a little unfun. Does that answer your question?
Yeah, sounds good. Thank you.
Perfect. What else? Please ask questions. This is your time to connect, to make sure that you're understanding this material. I see Jake raised. Go ahead, Jake.
In terms of the general code for finding the corner points, would it be feasible to just have a code that calculates the intersection points of every single possible combination of lines, or would that get out of hand incredibly quickly as the dimensions go up?
That's a good question. So when you're doing this by hand and you're being asked to find the corner points, you can probably just, solve it. And you can even ask it to find every single corner point. But the number of intersections could increase at a polynomial rate as the number of dimensions goes up. That's why, when we get to these higher dimensions, it gets big. That's why it's infeasible to check every single point. And so in those cases, that's where it's going to be super helpful to look for more the intersections that are important rather than all of them. But good question. It could be feasible to write that code for simpler examples.
So when doing homework, like question 3 on homework 1, how should we show our work for if we use Python or MATLAB?
Yeah, great question. So in this case, we have considered the following linear programming problem. The first step you have to do by hand. So you'll turn it into be a standard form linear program. And then in part 2, you're being asked to use the Excel solver or MATLAB or potentially Python. You're being asked to use these tools to solve it. And then in that case, what you can do is you can type up and you can say something like, you can attach your code, right? So in Google Colab, you can just share a link to the code that you've written. So you write code and then just put the Google Drive link and make sure you have sharing on. And then that can show that you used the tool. In your final submission, the best format would be to turn in like a PDF. So create a PDF of your work. You can even use this right here to create those PDFs, right? You can create a text block, and then in the text block, you can include images or different work. And then in your final PDF, just make sure that you have a link to this code with your answer. But definitely in your main submission, I don't want to have to click away into something else to see your answer. So when you submit to Gradescope, make sure your final answer is on the paper and the pages that you're showing me and submitting. But then if you want to link away to your work in a separate browser, then by all means do that.
Okay, thank you.
For sure. What else? See something in the chat. All right, so I have a direct message, but I can address this for everyone. So this is about problem 2 on the homework, and I'm being asked about, is the actual linear program a maximization of 9 values with 9 constraints? In this case, we do have 9 variables, but I'd encourage you to think a little bit carefully about, all our constraints. I think we might find that there's a little bit more than just 9 of them. Since today's webinar is about linear programming in Python, I won't jump too much more into that, but you're more than welcome to find me at my 9 a.m. office hours, and I'll gladly walk through that more in depth. Great question. Yes. One thing I like to one thing that's pretty cool is the applications of this. One thing that I made, it was a project I did with one of my friends, and it was with linear programming, and it was a scheduler, and it was for the math department. And what it does is it schedules the math TAs and PLAs into their shifts in the math tutoring center. And with that, it's a problem where you can think about, you want to maximize total preference. So we, the workers, will put in, right, our first, second, and third choice preferences. And then for each of the different shifts, and then there are constraints, right? Like each shift, we need to have between 2 and 3 workers. You know, each PLA can work 1 to 2 hours. Each TA can work 2 to 3 hours. The TAs need to have back-to-back shifts. And then all of a sudden you have a pretty complicated linear program that takes, you know, maybe 6, 7, 8 hours to do by hand. And then me and my friends last year, we went to the math department and we asked them, hey, can we make a linear program for you? And we did. So we created a linear program with the objective to maximize preference under those constraints. And then that's how they use it to schedule tutors to the math tutoring center. And it works very well. In a term, I asked for Monday from 1 to 2 in the tutoring center. That was my first choice. And then the model gave me my first choice. So that's one of the really cool applications of this, which is why I encourage you to pay attention, to learn, to think creatively about what can be done with linear programming in this course. This is super applicable in so many different places. And when you get to your course project, you'll have a couple options. If you think of something else that might go beyond that or might be different, go for it. Ask Professor Blaze. There really are so many opportunities with linear programming and optimization. So I encourage you all to think creatively and to come up with some cool projects as you see them. Okay. That's all I have for now, and that takes us to about an hour. I don't want to ramble on for too long. But that is going to make your life a lot easier. Later on in the course, there are pretty complicated homework problems where you're solving linear programs. They gave me a lot of grief. I was solving those by hand on my iPad with a bunch of fractions. It was not fun in any way, shape, or form. So I hope that this will make it easier for you to at least check your answers. Hopefully later on, I might be able to give a webinar on using Overleaf and LaTeX to write nice text. When I grade your work, you know, I love your, you know, little handwritten PDFs from your iPad. But I also like being able to read your work, and that's why, you know, writing in writing in LaTeX is such a really useful skill to have. So might do that webinar later on at another point. That'll make it easier for you to write nice text. In fact, I can show you a project that I've been working on. I've been writing a linear program for another research project I'm on. And I'll just show you that it might look a lot nicer if your linear program looks like this. Let's see, where's my share button? It might be a lot nicer if your linear program looks like this, rather than some mumbo jumbo that you wrote down on your iPad. So I might do a tutorial on doing that later. Okay. Any final comments or questions on that? Or anything I said today? All right, that's all I've got. If I can, I'll try to upload this recording to Canvas, and then I'll stop by class at some point to get a sense for if there's interest in a LaTeX webinar, and when a good time to have that might be. Thank you, everyone.
Thank you.
Thanks, Teddy.